The research question in our lab was, does the velocity of the ball bearing change in different solutions? The 3 different solutions we tested were water, dish soap, and corn syrup. The goal of our experiment was to find the relationship between velocity and the viscosity of these different solutions. Our main finding was that velocity is based off the logarithmic function of viscosity. This is a nonlinear relationship.
For our model, we defined our system schema as including the ball, the fluid, and the earth. The force of gravity from the earth acts downward on the ball, while the force of viscosity from the fluid acts upward, with the net force equaling the sum of the two. As the model progresses, the potential energy due to gravity gradually transforms into kinetic energy. Due to the law of conservation of energy, because no energy is leaving or entering the system, the size of the energy pie charts remain constant.
In our experiment, we dropped our ball bearing through 3 different solutions. We did 3 trials for each of our solutions. We then analyzed this motion using tracking software. We found the velocity using Excel by graphing the position versus time data given by tracker. We then compared our velocities to viscosities we found online, and we used Excel to graph these 2 different data points against each other. Once we had graphed them, we looked for linear and polynomial and logarithmic trend lines through the graph.
Using online sources, relative viscosities for each of the 3 liquids were found and used to compare with the relative velocities of each trial.
We graphed our 9 different data points in Excel, with viscosity on the x-axis and velocity on the y-axis. A more negative velocity is greater in magnitude, and this means it's moving faster, and the sign is negative because it's moving down towards Earth. We graphed it using a linear fit, but this had a really low correlation value, so we decided not to include this in the slide, but we show the second order polynomial and the logarithmic graph as well. The equations and correlation values are displayed on both of these graphs. While the polynomial graph has a slightly higher correlation value, we believe the logarithmic fit graph better models the real-world situation.
While both the parabolic and logarithmic graphs show a high correlation, the logarithmic model is much more indicative of a real-life scenario. As the viscosity of the solution increases, the velocity of the particle gets closer and closer to zero. A higher velocity correlates with the stronger IMFs in the solution, meaning the attractive forces between the particles of solution are more difficult to separate, which slows down the ball bearing as it descends.
There were multiple sources of error in this experiment. One of them could have been the ball bouncing off the side of the tube while we were dropping it through the solution. Another source of error was the ball moving too quickly through the water. We had very few data points for position, which then gave us a less quality velocity graph, which is then a less quality velocity versus viscosity graph. To improve this experiment in the future, we'd like to test more solutions. This would help us differentiate if the parabolic or the logarithmic trend graph better matches the overall trend. Another thing that could be done to improve future experiments would be to make sure to drop the ball bearing from the meniscus of the fluid each time. Some of our experiments were being dropped above the solution, and we are worried this could have impacted the overall velocity as it's speeding up through the air instead. However, overall, we are fairly confident in our lab, and we had a great time learning physics.